first speaker in this session will be Daniel Bladow from Gonzaga University. He's been working under the direction of Sean McCulloch here at Ohio Wesleyan this summer, and he'll be talking about artificial intelligence of modern war games, Battle Line.
So, hi, I'm Daniel. I've been working with Dr. Sean McCulloch, as HK said. What I've been working on over the summer is developing an artificial intelligence to play a game called Battle Line. Before I dive into what I've actually been doing, I'm going to start by giving an overview of the game itself so that you have an idea of what I'm actually doing. There we go. So, as far as the game, what you're essentially doing is playing 9 3-card poker hands at the same time. And what we call each of these poker cards, we call them flags. So there are 9 flags. On each of these flags, the hand you are going for, we call that the formation you go for. So if you're going for a straight flush, which is 3 consecutive cards of the same suit, that is the formation type. As far as the cards you're using to play the game, it is a 60-card troop deck. So there are 6 suits, number values 1 through 10. There's an additional tactic deck. It's 10 cards, and each of the cards mess with the rules of the game. So I'll get into a few examples of some of the type of tactic cards in a moment. Continuing on with how to actually play the game, you're trying to win these flags, so we call that claiming a flag. You can claim a flag when both players have finished their formation. You figure out who's made the better formation, you can claim it. Or if one player has finished their formation, and they can prove that no matter what, their formation is unbeatable, you can claim the flag early. In order to win the game, you must claim 5 of the 9 flags, or any 3 flags in a row. An additional note is that flags can only be claimed at the beginning of your turn. As far as the tactic cards go, some of them change the rules to how you claim an individual flag. And another note about tactic cards is once you have played more tactic cards than your opponent, you cannot play another one. So, as far as the rank of formations, on the far left, you see that player 1 is going for a blue 5-6. So player 1 is attempting to complete a straight flush. Player 2 has played 2 10s. Player 2 is going for a 3 of a kind. If player 1 completes the straight flush, player 1 will be able to claim the flag because no matter what, a straight flush will be a 3 of a kind. Now, when we're talking about formations of the same rank, in this example, we have player 2 going for 3 of a kind 9s, player 1 going for 3 of a kind 4s. The higher sum always wins, so 3 9s is a higher sum than 3 4s. When you're looking at straight flushes, a 7 high straight flush would be a 5 high straight flush. And here I have 3 examples of tactic cards. First, I'm going to start by talking about the mud card. This is one that changes the rules to claiming an individual flag. So like I said, your formations are 3 cards. By playing this mud card, your formation is now for 4. So if I am going for a straight flush and the mud card is on that flag, I now have to come up with 4 consecutive cards of the same suit. In the middle, we have the traitor card. The traitor card allows you to steal a card from your opponent's side and play it on yours. You must both steal it and play the card in the same turn. Additionally, you cannot steal a card from any flag that has already been claimed. So like if you've won a flag, you can't say, I'm going to play the traitor. You've no longer won it. Once you've won a flag, you've won that flag. Lastly, the shield bearer is an example of a wild card. It can be a 1, 2, or a 3 of any suit. So as far as flag claiming, what we note here is player 1 has finished a 3 high straight flush. Player 2 has played the purple 4 and the shield bearer card. What we can also see over here is that player 2 has played the purple 2, and we also have the purple 5 out. So normally, if that shield bearer card were not on that 3rd flag, player 2 could not complete any straight flush, and player 1 could claim the flag. However, being the fact that that shield bearer is out there, there's still the purple 3 left. So if player 2 is able to draw that purple 3 and play it, player 2 will be able to win that flag with a 4 high straight flush. So, as far as our approach to playing this game, we've applied this idea of probabilities, that we can give the computer an understanding of this mathematical reasoning. The computer can apply these probabilities and make decisions based on that. So what we're really trying to do by applying probabilities is avoiding game state traversals. Something that commonly happens when you're playing games with AI is you're traversing through different game states and options, and we're completely avoiding that by applying probabilities. An additional note we have is all of the strategy is based on math, so the computer has reasons for making these moves. They're not just traversals or arbitrary. And lastly, when I'm talking about an autonomous approach to playing the game and avoiding ad hoc strategic knowledge, I'm talking about the computer applying these mathematical principles, and I'm not imposing my knowledge of how to play the game on the computer. So clearly, I know that a straight flush is better than a 3 of a kind, and I'm avoiding telling the computer that that's the case by giving it these probabilities. So these are the two mathematical principles we use. The first one is the union of independent events. So we mainly apply this one when we're looking at creating different types of formations on a flag, or when we're looking at winning the game, because to win the game, it's any unique combination of any 5 flags or any 3 in a row, so that's an application of the union. The second one we use is called the hypergeometric distribution. Fancy name, we apply it in a simpler way. We're using it to determine the chance of drawing a card. We make the assumption that given the troop deck, either player 1 or player 2 will eventually draw all the cards. So the troop deck will become exhausted. So eventually every card will be drawn by either player 1 or player 2. As far as our base algorithm, what we're looking at is the computer's hand, and the computer is going to look at every card in the hand, and then consider playing that card on every single flag. So even if we know as the user that it's a bad move, we're going to let the computer decide that on its own. So when we're looking at scoring this card on a certain flag, we're scoring 4 different things. First, we're going to score the chance of actually winning that flag. And then we're going to score the chance of winning the game by the score based on that flag. And then these last two, we're going to look at the chance of drawing a card that the computer wants, and the chance of drawing a card that the opponent wants. Now when I'm saying like good card or wants, the way that we've quantified that is by saying any card that will guarantee a win for player 2 or player 1, that's what we say good card. So there are certain formations that will guarantee a win on a flag. Any cards toward those formations are good cards. So as far as calculating the chance of winning the flag, we start by calculating the different types of formations. Specifically, we calculate the top 13 formations. And then for each formation, we score the percent chance that the opponent will be able to make something better. And then we're going to look at the computer completing the formation that the computer is going for. And if you see here, we have 1 minus score, because first we calculate the chance of the opponent winning, and then to know the chance of us winning is our completion 1 minus, so that we get the negation of that. And then we have the flag 1%, which is the chance of any of our 13 formations winning. And then we have the game 1%, which, like I said, is the chance of any unique combination, 5 of the 9 flags that result in a win, or any 3 in a row. So there are also the tactic cards. This is the general gist. I'm going to not really go into the numbers, but what the computer does when it's looking at tactic cards is it'll play them aggressively if it guarantees a win on a flag. The computer will play them defensively most of the time. So what we have at the very bottom is if 1% goes from 0 to anything, we'll play a tactic card. Most of the time it goes from 0 to something decent, so it's not like we're going from 0 to 5, because the tactic cards tend to be very powerful. So aggressively when we're playing them, if it guarantees one, defensively in the other cases. And then these are two of the biggest challenges we have had with applying probabilities to the game of Battle Line. First of all, there's this scoring an empty flag. And the problem with scoring an empty flag is that the top 13 formations are several different 10, 9, and 8 high straight flushes, which isn't necessarily realistic. Because if I haven't played a card on a flag, what these formations would say is that I could make 4 different 10 high straight flushes. However, once I play a card, I can now only make 1 10 high straight flush. So the way that we currently attempt to solve this issue is we'll look through the set of cards that could eventually be drawn, so all of the unknown cards, and we're going to take the best one, and invisibly we play it on the flag, and we use that score. And then another big problem we have is an understanding of how one flag state affects another. So I have an example for that. So what we want to note here is we have 2 6s down there, computer has 2 7s here, and then that yellow 8. The important thing about these flags is all of those 13 formations, there's a lot of overlap between them, and the computer doesn't realize how that negatively affects its score. For instance, this yellow 7 in its hand, it wants it on this flag, it wants it on the yellow 8, and it wants it on the blue 7. So by making any move, it realizes that the other 2 flags don't have as great of a chance of winning the game. So now it's like, oh great, what do I do? Because I don't want to play that yellow 7 because my other flags don't have it. So, in conclusion, we're applying probabilities to avoid ad hoc strategic knowledge and imposing my understanding of the game. We are using this based in math, so it has a backup in reasons. And then we also handle to avoid time-consuming game state traversals. And there is a potential of using this type of an algorithm to play it on weaker computers, maybe even cell phones. So I would like to thank Ohio Wesleyan University for sponsoring their REU program and the NSF for their money. It's fantastic. And in particular, Dr. Sean McCulloch for advising me so well. Okay.
Okay, questions for Daniel?
So you talked about how you calculate the top 13 flag formations.
Mhm.
Why 13? Why is that the number?
There we go. Okay, so there's two reasons. The first reason is that if we have a flag with just one card on it, the top 13 formations will be all the straight flushes and all ways that you can make a 3 of a kind. So if I have played an 8, I can make a 10, 9, and 8 high straight flush. And then there are 10 different 3 of a kind 8s that I can make. So by doing this, we'll see every single straight flush, every single 3 of a kind. And then the second key factor is that the number of formations we calculate is proportional to the time that it takes our AI to run the program. So if we wanted to do every single formation, when you counted the totals, and at the very beginning of the game, we're talking about 30,000 different types of formations. So that's why it's 13, because we'll catch all the important stuff.
So you found empirically that those 13 are usually sufficient?
Yes, yes. Before this summer, we were doing 4. And the problem with that is we would sometimes miss a key 3 of a kind. So we really need to catch all of the 3 of a kinds. Yes, Dr.
I've never played it before, so roughly speaking, as a human player, about how many things of this sort are you keeping in your head in your own sort of mental calculations as you play the game?
When I'm making decisions for just myself when I'm playing the game, I look at how many of that card is left, and then whether or not I can still go for a straight flush. So when I'm thinking about it, I don't look at any percents or try to calculate any percents. I just look at the number of cards left, the number, if there's any overlap with other flags. So unlike the computer, I wouldn't want to split up those 2 7s and the yellow 8. Does that answer your question?
I think so.
If you do want to play it and test it out, I'll have it up on my poster, 13. Play it, give it a shot. It's pretty fun.
Cool. Any other questions?
Thank
Okay,
you.
let's thank Daniel.